hear okay? It's okay. So, I know. So it's a really great pleasure for me to be here today, um, especially because of the special focus, a special honor. Sorry? Okay. Okay. So I'd like to say just a few words about Wellington. I never had too much professional relation with him or collaboration, but of course I have known him since I was a PhD student, and I have so many memories of him. He has very kind of this. I will use. You can hear me? It's okay. Right? So he was really a very distinctive mannerism and personality, Wellington, and for me that's how I remember him. He just had such a unique way of just being and interacting with you, and we've all had very nice experiences. I was on his boat once, so we had a conference in Anglo dos Reis, and I remember him dancing for Ho in Trieste at some point. So it's there's very nice thoughts associated with him. So it's really nice also to be in this meeting dedicated to his memory. So what I want to talk about is also closely related to Viana's conjecture that Wilton talked about yesterday, which is about C9-Bowen measures and the existence of C9-Bowen measures. So I will tackle the problem from a quite different point of view than Wilton did, but the two are somehow related in some way. And in particular, of course, since this conjecture about the existence of SRB measures, one of the things we're interested in is exactly what characterizes or what conditions are sufficient to give the existence of SRB measures. So the result I will present is in the context of two-dimensional for the moment. So I suppose that F is a C1 plus alpha diffil of a compact surface. And I will try to explain why, for the moment, we just have two dimensions. And so the main theorem, which is joint work with von Kleimenhager, myself and Yasha Pessin, is the following. So I'm going to write a chain of implications, and the first is in some sense the easiest, but it allows me to introduce a bit of notation, which unfortunately I have to write. So the existence of SRB measure implies the following geometric structures. So there exists a rectangle gamma, and I will explain in a second what that is, such that it satisfies the following properties. So A is that gamma belongs to lambda, where lambda is a non-uniformly hyperbolic set with some diameter of gamma is arbitrarily small. So I will put some other conditions, but let me start by giving some of these, explaining a little bit some of these terms as I go along, as I introduce them. So a non-uniformly hyperbolic set is a set with non-zero diapason of exponent. It would take me 5 minutes to write down the precise definition, so I will not do that. But it is a set that has some splitting but the splitting is only measurable in principle, right? It has an expanding direction and a contracting direction. And one of the main results of non-uniformly hyperbolic sets is that you have local stable and unstable manifolds at every point. And a rectangle is a set formed by the intersection of local stable and unstable manifolds. So it's a set with local product structure. So let me draw. So a rectangle looks something like this. So it is a collection of stable manifolds and a collection of unstable manifolds. Boundaries here. So this here is a local stable manifold P. This here is the local stable manifold of Q. And these are the local unstable manifolds. And this here is a collection of stable and unstable manifolds. So these rectangles like this is called local product structure because all of these stable and unstable manifolds have the same length. So if you take any 2 points here, then the stable manifold of one will intersect in a unique point, the unstable manifold of the other. That's the usual definition of having a local product structure. If in some cases,
you
like in
equal lengths after renormalization of the matrix.
Excuse me?
You said equal lengths. This is after renormalization of the matrix.
No. These are not. This is not at every point. This is in general. This is what I was just about to say. In some cases, in uniform hyperbolic, in a Nosov case, then in the Nosov case, then these might be every point might fill up this space. So this whole domain might be filled by stable and unstable manifolds. But in general, in the general non-uniformly hyperbolic set, this will just be a Cantor set of stable leaves and a Cantor set of unstable leaves. And in the gaps of this Cantor set, there will be lots of other smaller stable and unstable manifolds, because one of the key problems of the non-uniform, and this is a key point here, so with a non-uniform situation, is that the stable and unstable manifolds have arbitrarily small length. So here there will be lots of pieces of stable and unstable manifolds with small length. When I mean small length, I don't mean that they're chopped off. I mean that it might be an unstable manifold. It's small length when it's closed. So if you have a point x here, then the local stable or unstable manifold is in some sense that can be made precise, the piece of manifold before it folds. Okay, just for those of you who are not very familiar with this. So here you might have lots of complicated geometric structure in the gaps of the canvas. Okay? So we assume we have this, we assume the diameter is not, we don't assume. So this is a theorem about the fact that the existence of SRB measure implies this. And we have other properties. So we have the second property, which is that gamma is nice. This is a terminology we borrowed actually from the one-dimensional dynamics. And what we mean by this is that there exists PQ in gamma, which are these two endpoints, in fact, and such that gamma is contained in gamma PQ, which is by definition the region bounded by these stable and unstable manifolds. So let me just write with the source shorthand these four manifolds, and such that there exists some T that depend on gamma PQ, such that if you take such that the image Fn of Vs of P and Ps of Q intersection the interior of gamma PQ is empty, and the similar F minus n of the U of both PQ intersection the interior of gamma PQ is empty for all n greater than or equal to t. So what this is saying is that if you look at the images of these two, just the two boundaries, in some sense, of gamma, they never fall in the interior of this. So this is obviously true if P and Q are fixed points, for example. Right? If P and Q are fixed points, then the stable manifold just maps into itself. All the points converge to P, and none of this local unstable manifold ever intersects the interior. If P is a periodic point, then there exists some T for which this holds, obviously, because a periodic point, as long as this periodic point does not itself enter the interior of this, if this is a periodic point that stays outside, then there might be some time at which it comes very close, so this stable manifold might at some point intersect the interior, but after sufficient amount of time, the length of the image of the local stable manifold is so small that because the periodic point is at some finite distance from the boundary, that this holds. Okay, so it's a kind of generalization of the idea of nice intervals in one-dimensional dynamics. Then there's two more conditions. The second condition is that C is fat. So let me write. So it's useful to write gamma as CS intersection CU, where CS is just equal to all the union of all the stable manifolds, and CU is equal to the union of all the unstable manifolds. So this is just the foliation of stable manifolds, this is foliation of unstable manifold, and we say that gamma is fat if the Lebesgue measure of CS is positive. Okay, so those of you who are familiar with SRB measures, this is clearly that this happens. So it's basically the defining characteristic of SRB measure is that this family of stable leaves have positive Lebesgue measure. And finally, can you see down here? Is that okay? So finally we say that gamma is recurrent. So gamma is T strongly recurrent, by which we mean simply that every point in gamma returns with positive frequency. So, or even just with positive upper frequency. So the limit of 1 over n times the cardinality of the indexes I up to time n, such that Fit, so here it comes back at multiples of t, belongs to gamma. Okay, this is possible. At multiples of t. So there is just a small technicality about the fact that we need this recurrence to be at multiples of t, where t is this one here, connected to the nice domain. Okay, so these are the conditions. So for those of you who are
This is for every x in...
for all x in gamma, yes. So I will say more in a little while about how natural or artificial I think these predictions are. Let me complete the statement of this result. Is that what we're going to show actually is that these conditions imply that there exists a Young tower with integrable return times. In fact, we will show that this is not just integrable return times, but this kind of it's a kind of first return time. First return time that is a multiple of t. First t return time inducing time. And this is a Young power, so by standard results of Lysen-Young, this will imply that there exists an SRV measure. So this is what we call this a kind of characterization of SRV measure. We show that these conditions are both necessary and sufficient. What we are most interested in, the most non-trivial part, is this one here, which is what I'm going to concentrate on. So the fact that SRV measure implies this is a one-page. It's a few standard facts from hyperbolic dynamics. You can do it. Let me just make one comment: is that this, we don't really need this in this particular case. For this implication, we just need sufficiently small. Okay, so for this particular implication, we need to assume that there exists a rectangle which belongs to a hyperbolic set with some sufficiently small diameter, which comes out explicitly from the calculations, and we need to suppose that this rectangle is nice, fat, and recurrent in the sense.
Stefano,
Yes.
being the SRV measure is used just in C?
Yes. Yes. Yes, so we have some corollaries which I will not go into, but we have some corollaries that work for any hyperbolic measure. Okay, so these are let me try to organize this information a little bit in a way that makes it a bit easier to digest it. And let me say that we divided this proof. So I'm going to, this is the proof. This is the implication that I'm going to concentrate here, which is the most important implication. And I'm going to divide it into two theorems. Theorem 1, that says that A plus B implies a property that I call the hyperbolic branch property, which I will describe in a second. And theorem 2 says that if gamma is nice, sorry, we don't need nice, let's incorporate it in that. So if gamma is fat and recurrent, fat, T strongly recurrent, plus hyperbolic branch property, this implies a Young power. Okay, implies that. So the reason I want to split it like this is because this is really the main, this hyperbolic branch property is the only places where we really use conditions A and B, including the fact that gamma belongs to a globally invariant, non-uniformly hyperbolic set, and the fact that gamma is nice. They're both only used for the hyperbolic branch property. And I want to emphasize that because the hyperbolic branch property is something that in principle you could hope to verify in specific cases independently of these two assumptions. Right? In particular, independently of the fact that you already have some non-uniformly hyperbolic set. If you imagine in some situation like in the Henon map, for example, where you don't know a priori that you have a hyperbolic set, I want to emphasize that our techniques does not really require that. There's some cases where you can show some property, you can still construct a rectangle in some sense directly because of information you have about the system, and then all you're left with is a hyperbolic branch property, which is crucial and highly non-trivial, and the other two which are kind of relatively elementary. So let me say what hyperbolic branch property is. Let me first, for simplicity, I will just assume, for simplicity, let t equals 1. There's nothing, it's just just makes the notation more complicated to have arbitrary p. So we assume that p and q are fixed points. Okay, in which case this is easily assumed. This is equals 1. So to define the hyperbolic branch property, I need to define what an almost return is. So x has an almost return to gamma. So I take a point x here in gamma, x is in gamma, and if at some point it comes back to another point of gamma that is clearly a return, and I would say that it has an almost return if it comes back somewhere inside gamma pq, and the image of its unstable manifold intersects one of the local unstable manifolds that we find gamma. And so this is f tau of x, and this here is f tau of vs of x. So, more specifically, if almost return to gamma at time, let's say tau greater than 0, if f tau of x belongs to gamma pq, so it falls inside this domain, and there exists some y in gamma, okay, such that f tau of vs of x intersects vu of y. This is an almost return. This is what looks like a technical detail, but it tends to be crucial in our case to introduce this recurrence because a priori, because this will, okay, I'm going to explain how we're going to use this. So let me say what the hyperbolic branch property is here. So we say that gamma has the hyperbolic branch property if for all x with an almost return to gamma at time tau, there exists stable strip C hat S, and unstable strip, I will say what this means, unstable strip C hat U. In fact, let me just draw this picture. So we say it has a hyperbolic branch property. So we know that x has an almost return, and we want to know a little bit about the geometry of these returns. And the hyperbolic branch is saying that we have some stable strip, which means some full-length strip. Formally it's defined by saying that its boundaries are full-length stable strips in some way, but this is intuitively clear, such that its image is an unstable strip. Okay, so this maps to this unstable. That's called a hyperbolic branch, and it's hyperbolic such that f tau of C hat S is equal to C hat U, and f tau from C hat S to C hat U is uniformly hyperbolic. Okay, with some constants that don't depend on x or the return or whatever. Some kind of uniform hyperbolic. So this is highly non-trivial, this hyperbolic branch property, and the proof of the fact that these two properties imply the hyperbolic branch property is a significant, it's about more than half of our paper is dedicated to this part. This is a generalization of what is known sometimes as cutoffs, as a result of cutoff, which applies to actual returns, right? If x belongs to this rectangle and it returns to another point of the rectangle, then there's a kind of version of this which applies to cutoff in the context of the general framework of Lyapunov charts and the terminology of non-uniform hyperbolic system. There's two main variations on that here. First of all, is the crucial one is that it is almost return, and this requires a fairly significant generalization of Katoff's result, and in our opinion is a result of independent interest in the theory of non-uniform hyperbolic dynamics. And then we use the fact that it's nice in a crucial way to restrict, because you initially prove the theorem in the terms of Lyapunov charts, which is these coordinate changes that you have there, and then you have to restrict. And this, so maybe I should have emphasized, so what these belong to gamma PQ, and this also belongs to gamma PQ, which is not obvious. Imagine that you start with a point that is very, very close to the boundary, then you can say, okay, if I take a point that's very close, and then it has this almost return, okay, you might have this kind of hyperbolicity, but maybe the hyperbolic branch will, the slip will come outside, right? So using the nice property allows us to say that the slip, whatever the slip is at every almost return, must be definitely contained inside gamma PQ. And then I forgot one more property, is that these, a very important property that also comes from the niceness, is that any two such slips, for any two such branches, for any two such hyperbolic branches, the corresponding slips are nested or disjoint. This is also an essential point for our construction, and this also follows from the nice property. The nice property, as you know, has this kind of gives these nested or disjoint results, and this means that if whatever point you have, if you have another point here that has another return, possibly another different return, you look at the unstable strip of X, you look at the unstable strip of X prime, and they're either nested or disjoint. So it gives some kind of significant geometric structure. So this is what I call the hyperbolic branch point. So what I want to describe instead is the second part that assumes that gamma is fat, but mainly the hyperbolic branch property X. Both the fatness and the strong recurrence are things that we will use only at the very end of the construction. What I want to describe is how the hyperbolic branch property is used in a fundamental way to construct a Young tower. Right? I want to describe this construction because it's something that I think is very nice. It's, I think, quite a new way of constructing Young towers. Anyone who has this experience knows that Young towers are, in general, very highly non-trivial to construct. And often they need a lot of specific information, and what we are doing here is now having a very little structure, right? All this supposes that we have a rectangle that has a hyperbolic branch point, essentially. Okay? And then we will use the fatness just to get the SRB measure, the strongly recurrent just to get the integrability of the return times. So how does this construction?
Stefan,
Yes.
just a question about what you erased now.
Yes.
Is that a one-dimensional property or codimension one? That kind of nestedness? Or?
Right. So that is the reason why so far our result is in 2 dimensions. Yes, that's well spotted. I meant to make that remark. So the reason we have for the moment a lot of our results apply to arbitrary dimensions, but the nice, we don't know how to generalize the concept, even the definition of nice in higher dimension.
I'm nice.
Yes, in your higher dimensional. Can you insert you in our paper directly? You're not fat, though. Yes. Okay. So how do we construct a Young tower? I will not, I will kind of, in principle I should give the formal definition of a Young tower, at least the topological structure, but I will assume that most of you more or less vaguely know it, and at the end I will say, when we've got the construction, I will say why what we have is a Young tower, so I will give a formal definition. First let me say that the key point about the hyperbolic branch property is that we now have a rectangle with a collection of branches, right? So the starting point is this: we have a rectangle. Don't worry about the facts. The strongly recurrent, for the moment, all we use about strongly recurrent is that almost every point has returns. In particular, it has almost returns, right? So real returns are special cases of almost returns. So the assumption that it's strongly recurrent in particular means that every point comes back. So because of the hyperbolic branch property, every point, every time it comes back, it gives rise to a hyperbolic branch. So we have a family of hyperbolic branches, okay? And so let me write it like this. So let n tau be the set of all times, this is the set of all times for which there exists some almost return, such that there exists some x and with almost return at time I. And then notice that because this is a compact manifold, because the derivative is finite, it's not so difficult to check that for a given time there can only be a finite number of slips, a finite number of hyperbolic branches, right? So if you fix the time, okay, this point might have a return at time tau, so time I. This other point might also have a return and it might give rise to another hyperbolic branch, but at each time there can only be a finite number, right? So we can index I is equal to all the indexes ij, where I belongs to n tau, and j is the number of hyperbolic branches that exist here. So j belongs from 1 to some ki, right? Where ki is the number of hyperbolic branches which has return time.
Are you obliged to know all of them, or if you have a beginner's connection, you are happy?
At the moment we use all of them, but we're going to...
Do you have to?
You need to make sure you take all the, at some point towards the end we will take all the highest, all the biggest ones. So I will use, you're going a bit ahead of myself, but we will use the nested and disjoint property to show that there's a partial order on all the slips, and we will take the maximal ones. So we need to make sure at least those are there. Okay, I think it will become clearer when we do it. But at the moment we know we have them all, we know we have them, and let's let C be exactly the collection of all such hyperbolic branches. Right? So F I C hat S to C hat U I J, okay, where IJ belongs to 1. So this is the collection of all hyperbolic branches, and what I want to, the way I want to see this is as a generalization of the standard horseshoe, right? So if you think about it, this, in the horseshoe you just have 2 hyperbolic branches, right? Or at least just a finite number, and they all have the same return time. So this, in a standard horseshoe, you could have one here, and then you could have another hyperbolic branch here, and that gives a horseshoe. Okay? And they both come back at the same time. Here we just have a much larger collection. We just have lots of hyperbolic branches, but think of it as exactly the kind of hyperbolic branches you have in the horseshoe. Okay? But you have an infinite number, and you have nested inside each other. They're not disjoint and they all come back at different times. Okay? So things are a little bit more complicated, but we actually want to think very much like in the horseshoe. What do you do when you have the horseshoe? You define the maximal invariant set of the horseshoe, right? So you define the set of points that stay inside this strip. So when you have a horseshoe, you have two vertical strips, and you often, one of the ways in which the horseshoe is constructed says, consider the set of points that stay inside these two strips for the whole time. We want to do basically the same thing, okay? But of course, what does that mean exactly? Because this point here has an almost return, so it belongs to some stable strip that has, to some hyperbolic branch that has return time tau. But of course, if you wait longer, it will have other returns, so it is inside a nested sequence of lots of strips. And there might also be some nearby points that have strips. It might belong to some strips connected to almost return of nearby points. So in general, every point would belong to lots of strips. So how do we decide? Depending on which strip you choose, it might be, for example, that when it comes back, it lands inside one of these strips or it lands inside the gaps. Yeah? If you take the union of all these stable strips, they will, so maybe it's useful to draw again another version of this picture. So here we have this our rectangle, and then we have all our strips. So we have one strip here, we have lots of strips, but the union of all these strips does not cover, in general, the whole space. There will be gaps. So now I could take this point here, x, so this is a strip that maps, say here, okay, and I take the image that we call this point z, and suppose the image falls here. So this is f tau of z, where tau is the return time of this particular hyperbolic branch. So now it looks like f tau of x falls outside the union of strips. So maybe it does not belong to the maximal invariant set, so we need to throw this point away. Right? It does not belong to the maximal invariant. But I say, wait a second, maybe z belongs to lots of strips. Suppose that z actually belongs also to a smaller strip. Okay, maybe maybe z belongs to some smaller strip, which comes back after some longer time. Right, it comes back here, and maybe when you look at z after this time, this is some f tau prime, right, where tau prime is bigger than tau, and then maybe if we iterate it by tau prime, then it falls in here. Then this is f tau prime of z. Okay, so that's good. Okay, so we actually fell inside one of the other strips, and in principle we can continue, right? We can check. What about this point? Now it belongs to this strip, and we iterate it by this image, but maybe it falls outside, but maybe it belongs to some other strip because it belongs to there where it falls inside the collection of strips. Okay, so basically we take all the points for which there exists a choice of return times such that it keeps falling inside the strips. Let me try to write it quickly, but a bit more precisely. So definition, we say that H plus, which is a sequence of IMJM, with IJM in I, IMJM in I, n equals 0 to infinity. Okay, is called is a forward hyperbolic sequence. Is a forward hyperbolic sequence if x belongs to C hat S I0 J0. So this indexes the stable state. Remember, we have this collection of unstable of hyperbolic branches indexed by I. So we take a point x that belongs to one of these strips, and then we want to make sure that every time you iterate them, it falls in another strip. So and for all n greater than or equal to 1, we have that f of I0 plus I1 plus IM minus 1 of x belongs to C hat S IM JM. Okay, this takes a little while to get your head around the exact indexing, but all this is saying is that you're now indexing the specific choices that you make of the return of the times for this point, and every time when you apply one more iterate by the sequence, then it falls inside a stable strip that is indexed by this, and then you iterate again by this IM, and then it falls into the stable strip C hat SIM plus 1 JM plus 1, and so on. Right? So this point has some choice of time so that it always falls inside. Okay? And then you can do, obviously I will not write it, but you can do the same thing for the backward time, and then you can have H is equal to H minus H plus is a hyperbolic sequence if you can do it both in forward and backward time. Okay. So this a given point may or may not have a hyperbolic sequence, right? It may or may not be possible. As I said, it could be that this particular point always, whatever choice you make, it always falls outside the strip, so it does not belong to the maximal invariant set. So we use this to define the maximal invariant set, simply as all the points who have for which this is possible. So we define a new set gamma equals the set of points x in gamma PQ such that x has a hyperbolic sequence. Well, we can actually, here we can define here, CS is a set of points that x has a forward hyperbolic sequence, and then we define CU. This is a set of points.
Do you need sometimes the CS of PQ? Is it a universal CS or?
Sorry, I realize now, let me call it C, this is, because I use CS before for the gamma, right? So let me call C tilde S and C tilde U, x in gamma PQ, such that x has a backward hyperbolic sequence. Okay, and then let me define gamma tilde is equal to C tilde S intersection C tilde U.
So does it depend on PQ?
Well, it depends on this domain. This is the domain that we fix.
Okay.
It does not depend directly on the points P and Q, but
Okay.
we fix the domain in which we're doing the construction.
Some others.
If you use a different domain, you would get a slightly different set of hyperbolic branches. So it's not that easy to believe that this is itself a rectangle, right? So if you think of the points that have a forward in exactly the same way that you do the construction for the horseshoe, where you get this nested sequence converging to some curves, you see that if you take all the points that have forward hyperbolic sequences, they will form exactly a stable curve, right? And if you take all the points that have the backward hyperbolic sequence, they will belong exactly to an unstable curve. Okay? So the lemma here, the proposition, the proposition is that gamma So gamma tilde contains gamma. Gamma was the initial rectangle that we used to define these hyperbolic branches. Every point, by the recurrence assumption, every point in gamma does return infinitely many times. So of course it will have both forward and backward times, so it will belong to gamma tilde. But in general, gamma tilde will be bigger than gamma, because that's the point of this construction, is that gamma was given a priori, but it may not have contained all the points that we wanted to contain. So gamma tilde is a nice recurrent rectangle. Okay, let me continue this here. So it's a nice recurrent rectangle. It has a particular property, it's kind of complete in some crucial way. So all almost returns are actual returns. So it's got a kind of a closure property, in the sense that if you have a point that has an almost return, because of the construction, that point has actually been added to this set. The collection of all corresponding hyperbolic branches is the same collection that we had before, is C. So now you have a new nice recurrent rectangle which has many more points, but if you take any almost return of this, then the branch you get is one of the existing collection of branches. This is a non-trivial and important crucial point about this. That's why we needed to start with almost returns. Okay, so, and the most important property is that for all ij in I, because this is the same collection of branches, we have the following property. We have that Csij, which is by definition f minus I of C hat U ij intersection Cs is contained in Cs, and C U ij, which is by definition Fi of C hat S ij intersection C U is contained in C. Okay, I'll just explain a little bit more of this, because then I've run out of time. But this is called a saturation, i.e. gamma tilde is saturated. So what does this mean? This means that when you look at the branch, so you look here, we've got our stable and unstable slips. We've got one branch, one hyperbolic branch here. So this is C hat S ij, and it maps to C hat U ij. So what does this say? This says that if you look at C hat U ij and you intersect with CS, which means that you take all the stable leaves. You take the intersect, you have all these stable leaves, and you take the stable leaves here. Right? So this is what this is. And then you take the pre-image of the stable leaves. Right? So you pull these back, and you get full-length stable leaves in here. What this is saying is that these stable leaves were already there. You're not adding anything new in here. Okay, so you have, this is a property that says that it's saturated. So you have everything you needed. Okay, you have all the leaves that you need connected. And then the proposition The next proposition, this is one, which I will just state and then I will finish, is that if gamma, so the first return, if gamma is saturated, then the first return time to gamma gives a Young tower. Yes.
What is written there? Almost returns are what?
Actual. Yes, that actual returns. Actual. So I don't have time to say anything more, but this is, in some sense, this in terms of the way the argument was developed, this actually was the first part that we got. Okay, we identified that this saturation condition is crucial, and once you have this saturation condition, amazingly, you get the Young tower structure. So the Young tower structure is something that says that now you take the Cantor set of these slips and they map to Cantor sets here. I don't have time to give the formal definition. But the amazing thing is this, is that if you have a rectangle with this saturation property, then you just take the first return time, and by miracle, this first return time actually is exactly in S subsets and U subsets, give S subsets in the terminology of Lyson-Young. And so we get a first return Young tower related to this. Okay? And because this is what we're aiming for, we realize when you're just given a rectangle, there's absolutely no reason for it to be saturated. And so this previous step, the hyperbolic branch and the method of construction of this is motivated by the fact that we're trying to get a saturated rectangle.
So, where at some point you have to deal. I assume you have to deal with distortion bounds and
Yes.
the angles. So, which part is it in your conditions A through D which will help you do that?
The fact that it belongs to a non-uniformly hyperbolic set. So in our proof of the hyperbolic branch property, right, so that every almost return gives a hyperbolic branch property, that's where we're using crucially the fact that we belong to a non-uniformly hyperbolic set, and so we have the Lyapunov coordinates, and we have estimates of hyperbolicity and distortion, which we get from there. Yes. So in the hyperbolic branch property, I said that you have uniform hyperbolicity in these branches. So if you have some other way to prove that, then you can just start with a hyperbolic branch property and do this whole construction.
But you say this follows from the SRB, from the existence of an SRB?
No, we don't need the existence of the SRB for that. I mean, the existence of the SRB...
But is it sufficient? I mean...
Yes. No, the SRB gives you this set, this lambda, which is the globally hyperbolic set, non-uniformly hyperbolic set. But in the definition of non-uniform hyperbolicity, you have some hyperbolicity constants which give you the distortion and hyperbolicity estimates that you made. So in the so we use that, we get the distortion properties from the hyperbolicity of the set that we are assuming.
Can I ask you? Do you have some type of for your different points, yes, and do you have to have to look at some type of synchronicity of having enough of them at a good time?
No, so maybe I meant to make that remark. Oh, and that reminds me of another remark I want to make. So thank you. So there's two remarks. One of them is that I did want to remark that for some reason we are able to avoid any explicit mention of any hyperbolic times or anything like that. It is somehow contained, of course, again, that is somehow implicit in the fact that we have a global uniformly hyperbolic set, and maybe the fact that we're in 2 dimensions, I don't know. But anyway, we do not
You
explicitly...
say uniformly or not?
Sorry?
You say uniformly.
Non-uniformly hyperbolic. And the second remark, I do want to give some credit. So the last part, the integrability of the return time, is due to the strong recurrence, and I want to thank Wilton for helping us to understand that that was the right assumption that we needed to get integrability of the return time. This is an argument that I think even mentioned something related to that. Yes, it's one of the theorems he mentioned says that if you have this strong frequency of visits, then you get integrable return times.
So if I understand correctly, the initial strips, they are not foliated by manifolds. There may be points with with small manifolds in between in one given strip. But then when you pass to the other strips, the tilde S, they are actually, by your hyperbolicity, they are foliated by stable and unstable manifolds. Is this true? Or?
So I'm sorry, I use the notation maybe not completely coherently. These are not strips. This is a family of local stable manifolds, C tilde S.
Okay, no, the initial strip is not necessarily foliated. There may be points with small...
Or the ones that you get from the hyperbolic branches.
In the beginning of hyperbolic branch. In the
Yes.
definition of hyperbolic branch.
Yes, you're right. So this you have a hyperbolic stable strip that maps to an unstable strip, but inside that you might have all kinds of stable things, yes.
And the return time, these return times, can you perhaps pass to a subset of cylinders where you have a common return time? If you get a large set of branches of strips which have a common return time? I mean, sometimes this helps.
I don't really understand.
You have, for points in a strip, you have one return time to get your Markov-like property, and for another strip you have another return time
Yes,
to Markov-like property.
yes.
So can you choose a big set of strips with a common return time?
I don't know. We do not need to.
You don't-
We do not need to do that. We just need the. I mean, because of the definition of niceness, we look at all strips already that have just return times that are multiple of t's, multiple of t.
Yes, but the multiple may
But
depend
yes,
on
that is just fixed once and for all, and then we don't need to worry about the relation between the different return times.
And the last thing is the relation with the Markov coding by Omri, Sadek, and Fogel.
He uses a completely different argument, completely different technique. I mean,
What was the question? So it's
A relation.
the relation between the work of Omri Sarig, where he constructs some Markov partitions for non-uniformly hyperbolic set. He uses a technique that is related to the shadowing, actually, that is the original Bowen's technique, and he shows that if you have a hyperbolic set, then you can cover it with a Markov partition, and as a corollary of our theorem applied to general hyperbolic measures, we also show that you can construct a first return Young tower for any hyperbolic measure. But it's a completely different argument, and he does not talk about SRB measures.
again?
Sorry? Sorry. Yes. Yes. There is some connections, but not really.